Imagine if every scientist had access to their very own personalized supercomputer. How much faster could they go? How much further would they get? At Microsoft, we're actually doing it. We're co-innovating with the world's leading scientific institutions like Pacific Northwest National Laboratory to reduce the impact of climate change, get to net zero emissions, and find new ways to create, to store, and use energy more efficiently.
We're joining forces with Microsoft to explore this convergence of artificial intelligence, high-performance computing in the cloud. And this is a shift that the world of science hasn't seen since really the dawn of supercomputing. And for us, it's helping us tackle these challenges in chemistry and material science that are embedded in the search for new energy storage solutions that the world needs.
My name is Vijay Murugesan. I'm a material scientist here in Pacific Northwest National Lab. My research is mostly focused on designing next-generation battery materials. Electricity generation needs to be renewable energy, but the renewable energy is not constant. It's sporadic, right? There's a lot of rain, or there's no sun, a lot of winds. Battery gives you an opportunity to store energy in a compact way and deliver it whenever, however you want.
Microsoft was really excited to work deeply with an organization that has strong roots in chemistry, material science, and how those disciplines relate to sustainability. Our goal was to work with PNNL to take the burden of exploring vast chemical or material spaces. Computational tools allow us to put the emphasis in the most promising parts of that discovery process. That's going to require a new way of doing chemistry that's computation first. Our team discovered a new electrolyte that uses 70% less lithium than shown in other industry announcements, because it replaces part of it with the earth-abundant compound, sodium. Azure Quantum Elements accelerated the initial phase of the discovery process. It took what would have been 20 years of computation and compressed it down into 1 week to identify the most promising candidates for later exploration.
Battery has multiple components. You are trying to put completely different type of materials together, and then you are asking them to work together as a synergetically. One part of the battery is called the lithium ion. Lithium is fast, and its ability to move even within solids is what makes lithium more attractive. But lithium is not something that you can easily go and dig it up. It's only available in certain geopolitical places. What the scientists have been thinking about is that how can we make it to the next stage, right? Can we use something else that can work as good as lithium, but without the baggage of their environmental and safety issues?
Tackling this approach through the traditional trial and error method is simply too time-consuming. The ability to narrow down the playing field from millions of potential combinations of elements and structures to dozens in just months, something that would have taken decades. The acceleration aspect of this can't be understated.
This co-innovation model has the potential to transform every discovery-based field. Chemistry and material science impact nearly all manufactured goods. So think of areas like pharma, life sciences, transportation, manufacturing. All of it is in play.
What we're most excited about at Pacific Northwest National Laboratory in this partnership with Microsoft is the opportunity to accelerate scientific discovery, not just in chemistry and material science. This is just where we're starting. When you think about the convergence of artificial intelligence models coupled with high-performance computing in the cloud, running alongside of co-pilots that are trained in specific scientific disciplines, and having all of that come to bear at the disposal of the individual researcher or the scientist, that's a paradigm shift.